So at this point in the class, we've learned about equilibrium. So what you now have in your toolbox is you know that for an object to be in equilibrium, the summation of the forces in the x direction must equal 0, the summation of the forces in the y direction must equal to 0, and the moments at any point along that object must also equal to 0. So now let's go ahead and just do an example. This is our first example in equilibrium, in which we have a beam. At point C, we have a roller support. At point A, we have a pin. You can see that the beam is kind of supported. There's a 0.5 foot distance. It's kind of like on a little hinge here with that pin at point A. Okay. Overall, you can see the beam would be 0.5 plus 10 plus 0.5, so the overall length of the beam is 11 feet. We have a load at point B of 2,000 pounds. And what we're trying to do is we're going to find the reactions at point A and the reactions at point C. Another item that we have, of course, is we have the beam weight here. We see that it's 26 pounds for every linear foot. So first thing I'll calculate is the overall beam weight. Okay, and I'm just going to take the 26 pounds per foot and multiply that by, again, you're going to have 0.5 plus 10, I'll just write it up, plus another 0.5 feet. Okay, so that's 11 times 26. So I'm going to call this just W, and it comes out to be 286 pounds. Okay. So the weight of the beam is 286 pounds. So let's go ahead and take this diagram, this original drawing, and simplify it as a free body diagram. At point A, of course, I have a pin, so I'm going to have two reactions. I'm going to have one in the y direction, I'll call A sub y. I'm going to have another one in the x direction, I'll call A sub x. Okay. Likewise, at point C, I've got a roller that's only going to give me a vertical support, so I'll call that C sub y. Okay, at point B, we were given a 2,000 pound force, point load. Okay. And then we also have this weight here that we have to incorporate, which is going to be in the middle of the beam. We'll work on that dimension in just a second. I'll just go ahead and put that as 286 pounds. Okay. Let's do these dimensions real quick just to make sure everything's clear. Again, this was that original dimension of 0.5 feet. Okay. We know I've got 10 feet from point A to point C. The center of the weight's going to be in the middle of this entire beam. If the entire beam is 11 feet, it would be 5.5 feet from this edge or 5 feet from point A. So I'm just going to go ahead and write that in. Okay. Over here, of course, I still have that 0.5 as before. And then the distance given here was 3 feet. Okay. So I've got 5.5 plus 0.5 is 6, plus 3 is 9. So this last little piece here, I'll just go ahead and write it in. That's 2 feet. I'll just put it this way. They'll be handy when we're taking moments. Okay? And like for all free body diagrams, I always write my reference axes. We're defining x to be positive going to the right, y to be positive going upward, and a counterclockwise moment is positive. Okay. So now that I've taken the original problem, solved for the weight of the beam, and have a free body diagram, I'm going to go ahead and use the equilibrium equations that we have available to us to solve this problem. Let's go after the low-hanging fruit first, so I'll go ahead and sum up forces in the x direction. Okay. So when I look at my free body diagram, I have AX, which I originally designated as going to the right. I have no other forces in the horizontal direction, so we can see from that that AX just has to be 0. Okay, so that pin is not supporting a horizontal load in this particular loading scenario. Okay. The next thing I'm going to do is I'm going to go ahead. Now I could sum up forces in the y direction, but if I do that right now, what I'm going to have is an AY that's unknown and a CY that's unknown. And so I'm going to have one equations and two unknowns, and that's not overly helpful. So I'm going to start by taking a moment. And you can take a moment anywhere along that beam, but the point that I'm going to choose is point A. Now the reason I'm choosing point A is because at this point you have two forces going through that point, AX and AY. So by taking the moment about point A, I essentially can use the fact that I know the 286 pound force at some distance, the 2,000 pound force at some distance, and I can isolate those known values with the unknown CY and solve for CY. So let's just go ahead and do that. So at point A, okay, I've got the first force I have is this 286 pound force, okay, and it's at a distance of 5 feet. Now we have to be careful with the direction of this moment, okay. From relative to point A, this 286 pound force is going to cause a clockwise moment, which would be negative. Okay, so I'm going to use minus 286 times 5 feet. Okay. Likewise, I'm going to have another negative moment coming from the 2,000 pound force. Okay, and that is at a distance of 5 plus 2 or 7 feet. Okay. And then the last force, of course, I have is the one we're solving for, and that's CY. Okay. The distance on that one is going to be 5 plus 2 plus 3 or 10 feet. Okay, and that is a positive moment, right? Because we assume it's going upward, and so relative to point A, that would be a counterclockwise moment. Okay. So when I solve for these, I get CY is equal to 1543 pounds. Okay, 1,543 pounds. Okay, that's upward. The direction that we assumed was correct. Now that I know this reaction at C, I can then go into my third equation, summation of the forces in the Y, which says that AY, which is positive, minus 286 minus 2,000, okay, plus my CY term, which we just solved for, has to balance out to 0. This gives me an AY value of 683 pounds. Okay, so to summarize, we started off with an original problem statement in which we had these two reactions, a pin and a roller. Okay, we knew the beam weight. We figured, or the beam weight per foot. We figured out the total weight of the beam. We simplified everything with a clear free body diagram that was showing our reactions and all the loads, and then we applied the three equations that we have available to us, the summation of the forces in the X, summation of the forces in the Y, and we took the moment about point A to solve for the three reactions. That concludes this example.